This video will begin our discussion of flux of a two-dimensional vector, so keep that in mind, two-dimensional vector field. So what flux means in this case, if we think about circulation, and let's relate it to the two. Circulation, let's look here. Circulation. Remember, this was a definition, I can't spell, I guess, circulation. Okay, circulation was some kind of weird measurement of the vector field being crossed with our tangent unit vector, right? It told me how much of the vector field actually pushes with us or faces us. Our flux is going to be the vector field cross a vector where n is orthogonal at C. To T. Orthogonal to T at C. So this circulation, this measured how much of the the vector field is pushing or at our face. What flux is since it's orthogonal, think about it at C going this way, this n vector would be there. So we're actually measuring, if I dot these two, F and N, I'm actually measuring how much of the force field crosses over path C moving that way. So this measures how much does the headwind and tailwind go, how much it pushes, how much does it holds me back, like pushes a headwind. A flux is all about crosswind. So it will actually measure, the flux in this case will be an outward flux, and it's going to measure how much wind crosses over point C, how much of the force is pushing C at an orthogonal angle. Well, this makes sense. If I can find an orthogonal N, then I can just take that dot product. Well, remember this is two-dimensional. Let's take a look at our picture down here. Two-dimensional, I can write my tangent unit vector, tangent unit vector, and then, and we're going to define it like this. Let's go ahead and write it here. Tx, ty, 0. So that's t, x component, y component, and then I know since it lives in the xy plane, z is 0, I get that. We also know that k is our unit vector. You may have not just put that together. I think when I first looked at it, I thought k was something they were making up. It's just our unit vector in direction of z positive. Take a look at the picture. T lives in the xy plane because our path lives in the xy plane. K lives straight up. Well, I could just take the cross product, and that will give me a vector n that sticks out. Now, a couple things. Due to the cross product in the right-hand rule, if you do t first, and then k goes up, n will always point to the right. So n is going to be defined if you're looking down on your path and it's going this way, n always pushes that way. It's always to the right if you're looking down at the orientation of your path. And this calculation will guarantee that. Now, a couple other things. We talked a whole lot about taking this vector field and dotting it with this n. And I want you to notice a couple things. All right, so if the angle between them is between 0 and pi over 2, that's straight up, then this dot product, if you remember from us doing dot products, will be greater than 0. The vectors work together. That's why it's positive. Now, if the angles are straight up, right, 0, not 0, so that means theta is pi over 2, which means that the dot product is 0. This means the measurement there, if it's a crosswind like that, it's giving me nothing, right? And then finally, the dot product, if it was bigger than this, right? Here's n, here's f, giving me that angle that is pi over 2 up to, we don't want pi over 2 to be included because we know pi over 2 spits out the 0, up to pi, the dot product is negative. So, check this out. If this is positive, there's a lot of crosswind coming across C. So if I took, let's do a path right up here. Here's my path, and I have this point. This is C. If this is the case, then there is a lot of crosswind of F approaching, going across there. If it's negative down here, then it pushes that way, across that way. So that it'll be a negative. So positive answers will tell me there's a lot going this way. Negative answers will tell me there's a lot going that way. And then if I get a 0 for a dot product, there is no flux. There's no crosswind. All right. Let's work into, we got one more thing we have to do, and then we'll do an example. We need to calculate this thing. So let's get that. It's a little bit of work. So bear with me. Let's go to that next page. All right, just to remind you, the tangent unit vector, we're going to call it tx, ty, and 0. And then we also have k here. K is 0, 0, 1. And they want us to find the cross product. So let's do that. I got I, j, k. And then I have tx, ty, and 0, and 0, 0, 1. And we got to figure out that cross product. All right, so covering up my first column and first row, I have, it's going to be ty minus 0, I, minus, covering up the j column, I got tx minus 0, j. And then covering up the k column, we get 0k. All right, so all this work, we get tyi minus txj. Okay, hold on to that. We're going to use it here in a moment. Okay, since t, our tangent unit vector, is defined the way it is, so let's define it. R prime of t divided by the magnitude of r prime of t. Since that's the case, then let me scoot this over. Sorry for my handwriting. I'm noticing it's looking pretty bad, so I'll try to clean that up a little. Then the tx, tangent unit vector, I mean, is equal to tx ty 0, and then we're going to rewrite this thing. This is the same thing, and this is just using the definition. X prime of t, y prime of t, 0, all over the magnitude of r prime of t. We're getting there. All right, now we're going to go back to what we came up with earlier. N is equal to ty of I minus tx of j. All right, we're going to rewrite this as, okay, ty is y prime of t over the magnitude r prime of t, comma, and it's a negative x prime of t over the magnitude r prime of t. All we're doing is replacing. I define t that way, then we use t to find n. All right, and we could actually, if I wanted to write that out a little further, I could as the vector y prime of t, negative x prime of t, all in a vector, divided by, and I only need to write my magnitude once. Cool. So we have that. Okay, so notice if we follow our definition here, c of f prime times n ds. All right, and I'm going to replace everything I have here. Okay, it's going to go from t equals a to b. And then I'm going to put f dotted with, and I have my new definition of n there. I got r prime of t, and then y prime of t, negative x prime of t. And then we still have ds. We can convert that to r prime magnitude. You can see where we're going here. R prime dt, leaving me with t equals a to t equals b, right? And that gives me f dotted with y prime of t minus x prime of t dt, right? Now f at the very top of this, and we kind of overlooked it, f is the vector fg, right? Those are just whatever's in f and whatever's in g. Well, it's a dot product, so this is the integral of t equals a, t equals b, and then we just dot product these. F y prime of t minus g times, and I guess we could put t's here. We want them in terms of t, gt times x prime of t dt. That is our definition of our flux integral. You won't have to derive this for me. I just like to not, I know there are a few things in Calc 3 where we've had to say, like curl we didn't derive, divergence we didn't derive, or anything like that. But there are a few things I think we need to derive. And in this case, that in thing is very important, because if not, I'm just like, boom, here's this example. This is how you do it. Okay, so here's the formal definition for the flux. We have our path xt and yt. over a vector field FG, sorry. And if I want to find the flux, all I got to do is take the dot product of those two things. It's really, and it's not really even a dot product, it's a minus. It gets weird, so we just need that definition. All right. I've talked about this throughout. The circulation is how much of a headwind or tailwind, while the flux is the crosswind as you're walking on some path. I would recommend reading that. Any of the text that I have in here, I don't like to read text to you because I feel like it's a waste of time, but I would recommend reading these and maybe go look at your book. Okay, so that is flux.